Hi friends, in this session I would like to discuss the control system questions which were asked in the Polytechnic TRB exam 2017. First question, a pair of roots has been moved further away from the imaginary axis. The relative stability of the system will be. Before checking the answer, I would like to recall something about the pole location for different cases on S-plane. And we know that S-plane is nothing but a complex plane consisting of two parts. One is real axis and another is a imaginary axis. A system is considered as a stable system when all of its poles are lying on the left hand side of the S-plane. It is said to be unstable when one or more poles of the system located on RHS of the S-plane. A pole omega n can be located by using these two values, del omega n and omega d is a natural damped frequency and omega n is a natural frequency. If we make the del value damping ratio as 0, the poles will move on to the imaginary axis. The poles will be located on the imaginary axis and the system will be considered as an undamped system. So there is no damping, del is 0. For the contradictory case, if we increase the value of del, the poles will move towards the real axis and it will be located on the real axis when the damping ratio is greater than 1. The system is considered as a over-damped system. Here, the two poles are located in different places on the real axis. Suppose the poles are located on the same place on the real axis means it is called as a duplex pole and the del value is equal to 1 and it is called as a critical damping. For the poles located in these areas, the value of del lies in between 0 and 1. For the system which has 0 del value will be more oscillatory because it oscillates in natural frequency. While reducing the value of del is equal to 0, the system is moving towards the imaginary axis. The relative stability of the system will be reduced. In the opposite case, if we increases the value of the del or a damping ratio, the poles are moving away from the imaginary axis. Natural frequency and oscillation are reduced to 0 and its relative stability is improved. So a system's relative stability will be improved when its poles moving away from the imaginary axis. Option C is the correct answer. Next question. The Nyquist plot of the first order system g of j omega is equal to 1 divided by 1 plus j omega t. So we know that Nyquist plot is a plot of magnitude and phase angle versus frequency. So we have to keep the frequency limits as 0 to infinity. Given function as 1 divided by 1 plus j of j omega. First we are going to take magnitude of j of j omega. While taking the magnitude, it will be 1 divided by root of 1 plus omega square into t square. Now we are going to substitute the limits, otherwise we are going to check the magnitude for different values of omega. We are starting from omega is equal to 0. While substituting 0, this will become 1, and while substituting the infinity, the magnitude of the function will be 0. For value of omega is equal to 0, the magnitude is 1. So if there is no frequency, magnitude will be full, and if the frequency goes to infinity, the magnitude will be 0. Next we are going to check the phase angle of the function g of j omega. The function consisting of one pole, we used to take the phase angle as minus tan inverse. It's a pole, right? So we have to put minus tan inverse of imaginary part divided by real part. So our imaginary part is omega t and real part is 1. First, while substituting 0, the value of phase angle will be 0, and for infinitive it is minus 90. So the option B is correct. For omega is equal to 0, magnitude is equal to 1. At omega is equal to infinity, it is 0. There is no magnitude. And while considering the phase angle, at omega is equal to 0, it is 0. So it's here. And for infinity frequency, this angle will become 90. And we have a shortcut for this. It's a plot of absolute values of magnitude and phase angle of open loop transfer function versus frequency on polar coordinates. So it is the plot of magnitude and phase angle versus frequency. This is type 0, type 1, type 2 and type 3. And this quadrant is considered as order 1, order 2, order 3, order 4. There is no pole at the origin and only one pole is there. So it's a type 0 order 1 system. So among the 4, this will come under the condition type 0 order 1. The system is represented by a block diagram shown in this figure. So this is the open loop transfer function and it has a feedback. You can write this as g of s is equal to 10 divided by s into s plus 1. And from this we can write the characteristics equation of transfer function. That is 1 plus g of s into h of s is equal to 0. We know the value of g of s and h of s is 1 because it's a negative feedback. For negative feedback we use positive value of h of s. So it is 1 plus 10 divided by s into s plus 1 is equal to 0. While reducing this, we will get the characteristics equation as the s square plus s plus 10 is equal to 0. Comparing this equation with the standard second order equation, then omega n square is equal to 10 and 2 del omega n is equal to 1. In this, del is the unknown value, so keeping the del on LHS, we'll move everything to RHS. This will be 1 divided by 2 omega n. We know that omega n square is equal to 10 and omega n is equal to root of 10. So the value of del is 0.15 and this value lies between 0 and 1. So this is a under-damped system. The next question, the transfer functions are given below. Which one represents the non-minimum phase transfer function? Non-minimum phase transfer function is nothing but a system in which one or more zeros lies in the origins of the S-plane and remaining all the poles and zeros lie on the LHS of the S-plane. In this we have only one transfer function like this, that is having a pole on RHS side. While drawing the pole 0 plot for this transfer function, the 1 0 s is equal to 1 lies on the RHS side and remaining poles are lies on left hand side of the S plane. So this is a non-minimum phase transfer function. Then a steady state error of type 1 system for unit step say input signal is equal to. So it's a type 1 system and the input signal is a unit step input. We have to find out the steady state error and formula for steady state error is limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. Here r of s is our input and it is given as unit step input. So s into 1 by s divided by 1 plus it's a type 1 system. Okay, a type 0 no pole at the origin, type 1 one pole at the origin. So how will be a type 1 system? It will be having one pole at origin and another at some other place. So it is a k transfer function of type 1 system is k divided by s into s plus 1 and we are going to substitute the s value as 0. K divided by 0 is infinitive. 1 plus infinitive is infinitive. 1 divided by infinitive is equal to 0. So the steady state error of the type 1 system for unit step input signal is 0 is option D. And instead of doing like this, we can use this table. From this table, we can write a steady state error of any type of system for any kind of inputs. We have values for type 0 step input and type 1 paramp input and type 2 parabolic input. For other than that, we'll be having infinitives here and zeros here. K is equal to limit s tends to 0 g of s into h of s. Next question. The total gain x4 divided by x1 of the signal flow graph shown in this figure is. A signal flow graph is given and we have to find out the transfer function of that. Nothing but output divided by input. So it's a transfer function of the signal flow graph. Today we use Mason gain formula for this and that is T is equal to 1 divided by del summation of K Pk into del is 1 minus sum of individual loop gains. Pk is the gain of the kth forward path. Del is the determinant of the graph, that is equal to 1 minus sum of individual loop gains plus sum of gain products of all the possible combination of two non-touching loop gains, and minus sum of gain products of three non-touching loop gains. And del k is about part of the signal flow graph which is not touch the forward path. So first we are going to find out the forward path gain. P1 is equal to, simply I have drawn the forward path law, that is A, B, C. So gain will be the multiplication of all the gains. So forward gain path is equal to A, B, C. And next we are going for the loop. So here we have only one loop, B, D. Del 1 is 1. Del is equal to 1 minus sum of individual loop gain. Here we have only one loop. So up to this is enough for us. And t is equal to x4 divided by x1. That is our transfer function is equal to x4 divided by x1. Forward path gain divided by del. So its forward path gain is A, B, C, and del is equal to 1 minus sum of individual loop gain is BT. So it is 1 minus BT. This is the answer.